Sorry. Our next speaker is Ming Hu from University of California, Santa Barbara. And he has a presentation on YouTube. So we will be starting that shortly.
My name is Ming, and I am a statistics PhD candidate at the University of California, Santa Barbara. First, I will introduce the background on renal disease and hemodialysis in the United States, as well as the challenges and innovations that we faced for our research. In the second part, I will introduce our novel fast Kalman filtering algorithm for Gaussian mixed effect state space models, as well as the joint modeling framework that we have built to model the individual time series and mortality. I will then go on to discuss some of the simulation examples and online prediction for mortality in our fourth and fifth section, and then finish with a discussion of our research. Renal disease, also known as chronic kidney disease, is a condition where the kidneys lose their function progressively over time. Over 26 million American adults suffer from different stages of CKD, and when they reach the end stage renal disease, which is also known as ESRD, the patients will need to undergo dialysis, which is going to be a connection between the patient and a machine called the dialyzer, and this is actually quite an expensive procedure, and because of the amount of patients affected by ESRD in the United States, this is now one of the top topics in medical research. In our study, we shall consider 5 longitudinal risk factors of mortality, including albumin, systolic blood pressure, intradialytic weight gain, neutrophil to lymphocyte ratio, and hemoglobin. And in figure 1, we are plotting the monthly averages of 10 randomly selected patients, of which 5 actually died during the dialysis treatment. And you can see in each subplot, we are plotting the trajectories for each month the patient is undergoing dialysis treatment. And once they reach the X, it means the patient has died. So we see quite some variability in the trajectories and also some seasonal changes for some patients. And this is an extra level of difficulty for our modeling. Furthermore, in the Kaplan-Meier survival plot, we also see that up to 40% of patients have died about 4 years into the dialysis treatment. So mortality is a key concern in research involving dialysis treatment. Our proposed joint model can handle many different longitudinal profiles and avoids the proportional hazard assumption commonly used in existing joint models. Our framework further allows to extract information from individual profiles and explore dynamic relationships within and between longitudinal variables, identify risk factors for mortality, and perform online prediction. And combining all of these functionalities, we may inform individualized clinical decisions for the medical experts based on predictions. And furthermore, our mixed effect state space model is useful for understanding the interactions between biological processes. In terms of the methodology, our new efficient computational method now scales linearly in the number of subjects, which allows for fitting the MESSM and the joint models over a large number of subjects. And the next slide is on our main model, which is the mixed effect state space model. And we are showing it in its vector form, where the first equation, known as the observation equation, connects the observation vector y, which is a stacked vector for the observation of each individual for individual 1 to m, and connects y to the latent state vector alpha, which is used to model the underlying biological process, which is unobserved and reflects the true health condition of the patient. And in the second equation, known as the state equation, we have alpha t plus 1 evolving based on alpha t, and this is assumed to follow a Gaussian distribution. And furthermore, our latent state vector alpha is composed of two parts. The first is the fixed effect latent vector part, denoted with U, and the second is the subject random effect latent vector part, denoted with V1 to Vm for each subject random effect. And we may further consider modeling with cubic splines for the population trends and OU process for the individual departures, because cubic splines incorporates the smoothness, and OU process is commonly used to model biological processes. We can also use local linear trend to model these, as well as other possible modeling choices. But for cubic spline and OU processes, we can build these assumptions into the transition matrix and covariance for disturbance terms in our model setup. We assume that for each subject, there is the same number of time points from 1 to n, and these time points are all equally spaced. So if we look at each single subject, this is a time series from 1 to n. Initial distributions are also assumed to be normal for our fixed effect latent state, and normal again for our subject random effect. The fixed effect is assumed to be mutually independent with the random effect, and their disturbance terms, as well as the observation disturbance, are mutually and serially independent. Finally, we simplify and assume that the covariance terms for these disturbance terms are going to be the same across all t, so no changes between different time points. Now, to model the within subject correlation for a longitudinal variable, we will use the random effects, VI. As for the relationships between different longitudinal variables, we will model them with a combination of transition matrices, selection matrices, and covariance matrices based on different setup of the model. So this allows for a lot of extra variability. The challenge is the dimension of the observation vector y and the state vector alpha are qm and du plus mdv, where q is the dimension of each yi here. So in our case, it should be 5, corresponding to the 5 clinical variables. And du is the dimension of the fixed effect latent state vector. dv is the dimension of the random effect latent state vector. So since du and dv are multiples of q, we can find the complexity in terms of space and time for computing the Kalman filtering is quadratic and cubic with respect to the number of subjects m. And because m is usually large in longitudinal studies, we can foresee that the conventional Kalman filter will be computationally infeasible over a large data set. Moreover, to the best of our knowledge, there is no existing work on using mixed effects state space models in jointly modeling the longitudinal variables and mortality. So this is the conventional Kalman filtering equations first developed back in the 1960s. And basically, the key idea is to find the filtering mean and covariance, as well as the prediction mean and covariance for the latent state based on observations up to the previous and current time point. The following theorem, which is our main contribution, takes the large matrices P, F, and the filtering covariance P, T given T, and dissects them into smaller matrices P0, P1, and a linear combination of P2 and P3. And because P0, P1, P2, P3 are independent of the number of subjects M, we can simplify we can reduce the space and time complexities into linear with respect to M. Thus, we can conduct mixed effect state space models with respect to large data sets with many different patients or subjects. Furthermore, if we conduct state smoothing instead of filtering, this will still be linear with respect to M. The complexity comparison is given in table 1 for clearer demonstration, and you can see that compared to the standard Kalman filter, our proposed Kalman filter is now linear in terms of M, thus greatly reducing the complexity needed for estimating the model. The joint modeling framework that we are proposing uses ZIT as the event indicator, taking value 1 if the terminal event, which in this case will be death, takes place during t-1 to t and 0 otherwise. And we further use SI to denote the censoring event. We assume that given the latent state and covariates, this terminal event will follow a Bernoulli distribution with probability pi I, and we are going to model pi I with a logistic regression based on the covariates xi and the latent states alpha I. And we now introduce a simulation study to illustrate the advantages of the proposed fast Kalman filtering algorithm, where we model without the regression term and with cubic splines for the fixed effects and OU process for the random effects in our MESSM, and using an unstructured time invariant error covariance to model the between subject relationship. We will further consider 6 choices for the number of subjects M, and this ranges from 100 to 1 million. And based on 100 simulation runs, we report in table 2 that our proposed Kalman filtering algorithm is significantly faster than the standard procedure. For example, if we consider 1 million patients in the medical dataset, the standard Kalman filtering will take a ridiculously long time, whereas our proposed procedure only takes less than 20 seconds. And nowadays, with the advancement in electronic health records, this the medical data sets used for learning is getting increasingly larger, and we are seeing very commonly data sets with more than 10,000 patients, usually in the number of 100,000. So this is quite a significant improvement. As for our real data application, we introduced the hemodialysis patient dataset, which considers a cohort of 5,700 end-stage renal disease patients collected from our medical collaborator, Fresenius Medical Care, during 2010 to 2014. Fresenius is one of the largest providers of dialysis care in the world, and we consider from this dataset 5 longitudinal key clinical variables: albumin, systolic blood pressure, IDWG, neutrophil to lymphocyte ratio, and hemoglobin. As for our survival submodel for the covariates X, we consider age, gender, whether the patient is diabetic, equilibrated KT over V ratio, and the type of vascular access, which describes the way the patient is connected to the dialyzer machine. We will further consider the 5 key clinical variables as the 5 entries in our observation vector, and the population trajectories are modeled with cubic splines and subject random effects by OU processes. The connection between albumin and mortality has been shown in separate clinical studies, and the weight gain also measures fluid retention, which is a major clinical concern in dialysis and a cause for cardiovascular mortality. Furthermore, clinical studies has found that the systolic blood pressure is of importance for predicting mortality in renal studies, mostly because intradialytic hypotension is going to cause death. Neutrophil to lymphocyte ratio is related to inflammation, and hemoglobin variability related to both inflammation and malnutrition. And these are key causes for death among dialysis patients. EKTV quantifies the dialysis treatment adequacy, and the vascular access contains 3 different types, with the traditional CVC access type as the baseline. Our parameter estimates from the model indicates that longitudinal variables ALB, IDWG, and NLR, as well as the survival covariates age, EKTV, and vascular access are significantly associated with mortality, whereas having lower albumin and EKTV and higher IDWG, NLR, and age will lead to higher death probability. And this corroborates with findings from separate clinical studies and also with our intuition as well, because you see people who retain more waste after dialysis and have and are more and are older are more likely to die during the dialysis treatment period. Furthermore, we have found that the newer AVF access type is going to lower mortality compared to the traditional one. So this is justification for the expensive switch from the old method to the new one. The parameters in the unstructured error covariance matrix have showed us that the positive correlation exists between HGB and ARB, as well as between HGB and the blood pressure. So based on all of these understanding, we have constructed, using our state space model capabilities, an online prediction method for our patients, and we are randomly selecting one individual who died 35 months into the dialysis treatment. And we are showing that based on given data, we may perform a filtering estimate based on our estimated model for this time series in order to indicate the upcoming clinical variable fluctuations for this patient. More importantly, the survival probability correctly picks up an upward trend for this patient and significantly increases to over 0.75 about 6 months before the patient dies. And each time point represents the probability of the patient dying within 6 months from this measurement date, based on available data up to this given time point. So this is of significance for medical experts in providing timely, individualized treatment ahead of fatal complications, and helps to lower mortality rate. Furthermore, we have also selected a patient who survived all 4 years of dialysis treatment, and the survival probability still correctly picks up this increasing trend, and we may further add a 6-month ahead dynamic prediction with 95% interval for this patient. So overall, our research can be used to conduct fast computation with respect to the number of subjects in a longitudinal dataset, and provides a powerful method for exploring and quantifying dynamic relationships between different longitudinal variables. our joint models also avoids the proportional hazard assumption used in conventional approaches and helps lower mortality among dialysis treatment with possibility of extension to include hospitalization on top of mortality. So we would like to thank our financial support from various grants and our collaborators, as well as my collaborator on this project, Dr. Luo and Professor Wang. And thank you very much for attending my talk.